All right, in this video, I just want to do a quick rundown of what the Newton's three laws are, a couple key terms that you want to make sure you pay attention to, and then look at some free body diagrams and be able to write the equations for those different scenarios. For the first law, a mathematical way to think about it is just that balanced forces do not cause acceleration. So that in our sum of all forces equation, all right, sum of all forces is equal to 0. All right, you're more familiar with the sum of all forces equals mass times acceleration. Well, if the forces are balanced, there is 0 acceleration, so m times 0 on the right-hand side would be 0. So when it's first law, we always want to make sure that we start out with the statement that the addition of all the forces are going to equal 0. A second variation of the law is this statement right here: an object at rest will remain at rest, and an object in motion will remain in motion. And then there's that extra part that says, unless acted upon by a net force or an external force, outside force, sometimes worded different ways. So it's really saying an object's going to stay in its current state of motion unless it's not. Unless it's the first law, an object at rest will remain at rest, unless it's the second law. So this part in parentheses is just to show that it's really not a part of the first law. With the first law, you definitely want to pay attention to some key terms. At rest, if it's not even moving, it can't be accelerating. Balanced forces is the first law, so it could say just balanced. Constant speed, no acceleration. Terminal velocity is a special term for when an object is falling at a constant speed because of the air resistance upwards. So like jumping out, doing skydiving, jumping out of the plane, you're going to speed up and accelerate going down, and then you open up your parachute, and there's more air resistance there that allows you to keep falling down, but at a constant speed. All right, with Newton's second law definition, unbalanced forces cause acceleration in the direction of the net, or unbalanced force. All right, so just knowing that if an object is accelerating, the forces have to be unbalanced. So when we write out our equation, our first statement for our equation, we would write that the sum of all forces here cause acceleration, ma. This also has some key terms. I mean, the obvious one is accelerate. If it says accelerate, it's got to be the second law. Speeding up, slowing down are examples of accelerating. And then coming to rest is another way to say slowing down. It's just going to say, hey, it ends at a 0 speed. All right, now with third law, for every action force, there is an equal and opposite reaction force. So force is all capitalized because if you remove that word force, you don't have the third law. The third law is only applied to forces in mechanics. So another way to say it that's a little bit more clear, if object A exerts a force on object B will exert an equal and opposite force on object A. And we kind of went through an example that was a little bit strange with this. Here we have the Earth. All right. And then we had the apple above the Earth there, right? And we labeled all the forces. Here we have the Earth pulling the apple down. So it's the force of Earth on the apple, all right? And the reaction force to that is, well, if the Earth pulls the apple down, then the apple has to pull the Earth upwards. So it would be the force of the apple on the Earth. They are object E on object A has to be equal to and opposite to force of A on E. And you can see the forces are opposite in direction, so it is the third law. Writing it out a little bit more mathematically is F of A on B equals the negative opposite force of B on A. Let's look at this situation here. So we play, whoa, car comes zooming in and then screeches to a halt at the very end. All right, so what type of scenario is this? Is this a first law or second law scenario? Well, the motion changed. It was moving with some speed, and then it decreased in speed and ended at rest. And that means that there had to have been an acceleration. So let's think about what the diagram's going to be. I'm going to get this thing zooming right there. Oh my God, it's too fast. Let's just leave it at the end. At any point where the car was, all right, looks exactly the same. We have our X and Y axis acting from its center, and we got to think about what forces are acting on this car as it is moving along that surface. Well, gravity is always acting, and that is acting downward, so we would include that mg on our diagram. But the object is not accelerating downward, so we have to think, what else is interacting with it? Why is it not going down? Well, there's a table there, and that table has to be exerting a force upwards so that there is no acceleration downward. There we go, the total up. Let's make that a little longer so that it seems to equal what's going down. Total up has to equal total down if there is no change in motion up and down. All right, now left and right, there was a change in motion. All right, what caused this car to stop? Well, in this case, it would be friction, all right? A real car, same thing, friction, brakes, all right? What direction would the force be acting in order to slow an object down? It has to be opposite the direction of motion. So we have a force that is going this way, and we will call that friction. It was moving to the right. What was pushing it to the right? Be careful, all right? Let's look at the video. Let's rewind the video. All right, as you saw it move, what was it in contact with? What is pushing it to the right? Nothing. All right, there's nothing there. You cannot identify anything. It does not exist. So those are all of the forces that are acting on it. So now we have to identify what law it is. All right, so we have sum of all the forces in the X and the sum of all forces in the Y. Let's do the Y first. Up and down, we've already established the car is not falling downwards, not accelerating. The normal force is holding it upwards from the surface. The up has to equal the down, and that is a sum of 0. In the X direction, it did change its motion, so there is acceleration there. All right. Now, we just sum up the forces that we have on our diagram. We have a upward force and a downward force. Okay, 2 forces. In the X direction, we only have that 1 force, so that actually makes it pretty easy. Now, if we're making to the right positive, all right, that would mean that this force is negative. You can actually choose what's positive and negative here. You can actually make the direction that it's accelerating positive and make actually the friction positive. I'm not going to do that right now. All right, so we would just write our equation, add up everything that is in the X. There is nothing to the right. There is something to the left, so we have minus the friction, because it's going to the left, has to equal mass times the acceleration, and that's it. Up and down, we have 2 forces that have to add together to be 0, right? So the right side doesn't change. We have 1 up, which is the normal force, and 1 down, minus the gravity. And those 2 have to equal each other, right? Fn equals mg in order for it to be balanced. All right, here we go. We have this guy hanging by 2 cords, and I'm going to draw my free body diagram off to the side. Our origin is the center of mass. We would have an X and a Y axis, not necessary to be drawn, and we have to label all of our forces. So we have 1 cord going off in that direction there, and another one that's at a little bit of a different angle. I'll label this one as T1 and T2. And we have gravity always pulling the object straight down. All right. Now T1 is at some angle theta, T2, and then T1 as well, theta 1. with the thetas, just like in projectile motion, we have to break them apart into their x and y components. So T1 has an x component going this way, and I'll call that T1x, and then it has a y component, T1y. On the right-hand side, we have T2 in the x direction and T2 in the y direction. All right, and anytime we have to solve for the x and y components, especially when we're drawn with respect to the x-axis, we always use cosine for the x and sine for the y. Next, we have to add up all the forces. So we're going to add up all the forces in the x direction. So I'm going to write a statement here that says, this is what I'm doing. I'm going to add up all the forces in the x. And then down here, I should be able to squeeze in the sum of all the forces in the y. And we have to state what law this is as well. So is the object accelerating? And you have to ask that in both directions. So left and right. Is this object changing its motion at all? No, it is at rest. It is not changing from that state. So left and right, it is not accelerating. The sum of all forces have to be 0 because everything's balanced. Same thing up and down. There is no change in motion up and down. The right-hand side has to be 0, no acceleration. And when we go down to the next line to really write out the relationship that we need to solve anything for this problem, the right-hand side always stays the same. So we're making our decision of what is going to end up on the right-hand side throughout the rest of the problem in that first step of what law is being applied. All right? Now we just sum up the forces that are pointing left and right. We go over to our diagram here. We can see that left and right, we drew them in green. We took the angles and broke them apart because we are bound by this two-dimensional system that we have to keep everything separated. So we have one to the right and one to the left. Right is positive, left is negative. If we were to add this and this together, we should get 0. So that means that the one to the left has to be negative. All right, so I'm just going to write it this way as T2x minus T1x. And that has to equal 0. And if you think about it, that makes sense. And if this minus that equals 0, all that's saying is that the x component of the tension in the right-hand chord has to equal the tension in the left-hand chord in that x direction. Now let's do the same thing in the y. We go over, we look, we have up component, down component, all right? So now we have 3 different forces up and down that we have to combine together. And remember that the direction of the direction the arrow points is going to determine whether it's plus or minus. So up is plus, down is minus. So we're going to write them according to their directions there. T1y plus T2y minus mg has to equal 0. The total upwards force has to equal the total downwards force in order for this object to remain in a balanced state. All right, so this plus this has to equal the total amount of gravity because gravity is not causing it to accelerate downward. We can take this one step further and plug in, how do you solve for these x components? Remember, x component, here's the angle, it's the adjacent side, that's the cosine, so we would take the tension that is in that chord right there along the direction times the cosine of that angle for it, and that would have to equal the same thing on the other side. And you got to keep track of your angles because they're not going to be the same. So subscripting the angles is very important as well. All right, same thing happens down here. So that T1 times now the sine of that angle plus T2 times the sine of that angle. And we'll just move this over just to say, again, that the total upwards force has to equal the total downwards force when this is a first law situation. All right, one more scenario here. Play the video. All right, this thing is on what's called an air track. So it's kind of like an air hockey table where there's air coming out of the rail there, and the cart is just floating on top of this lovely bed of air there. All right, so we look at it. We're trying to try to identify what forces are acting on it. All right, so what law is actually occurring there? Look at the motion. Motion is constant. It's moving with a constant speed. That's showing that the forces have to be balanced, left and right. What are the forces that are acting on it, left and right? All right, it's moving to the right. What is touching it? As you're watching the video, can you see anything acting on the cart to the right? No, you can't. There is no force pushing it to the right. So how is it moving and moving at a constant speed? Well, that just means that there is very little, if no, friction acting to the left on the object. So left and right, there are no forces. So the only forces acting on this cart are gravity down and the rail upwards, which is the normal force. There is nothing left and right. So in the sum of all the forces in the x direction, it would still equal 0. It's just we would not be able to write anything down on the left-hand side because there are no forces that exist. On the y-axis, up and down, is the object's motion changing up and down? No. It's staying at the same exact height the entire time. There is no change in its motion. So we have one force up, normal force, minus one force down, gravity, and then the right-hand side doesn't change because we put all of the thought into what laws are being applied in the first statement after our free body diagram.